Hello everyone, my name is Muhammad Rafli Ramadhani. I'm from Sampurna University, and in this video I would like to explain to you about the mechanical behavior of engineering application deflection of the beam. Next, we have the first case study, which is the case study 1. We have the question. For the beam and loading shown, knowing that A equals to 2 meter, W equals to 50 kilonewton per meter, and E equals to 200 GPa. And we ask to determine the A, the slope at support A, B, the deflection at point C. And we have the strategy to solve this question. First, we should identify the unknown. We should identify the known. Second, draw the FBD. Third, calculate the reaction force. Fourth, divide the beam using superposition method and find the elastic curve. Fifth, find the slope. And sixth, find the deflection of the beam. In this case, we have the simply supported beam, which has the condition of x equals to 0, y equals to 0, x equals to L, y equals to 0, x equals to A, y equals to y, x equals to A, dy over dx equals to dy over dx. The first step is we should identify the knowns. So we have A equals to 2 meter, W equals to 50 kilonewton per meter, E equals to 200 GPa, and since it is wide flange beam, we take a look on the appendix that I equals to 84.9 times 10 to the power of minus 6 meter to the power of 4 for the W 310 times 38.7 wide flange beam. And for the length, we have 6 meter, which is equals to 3A. And we also know that the support at point A is a pin support and at point B is a roller support. And the second step, we should draw the free body diagram of the beam. First, we have RAY, RAX, RBY, and for this one, we have the distributed force at the beam. So we have WA in the middle of the distributed force. So we have the length is A over 2. Next, we should calculate the reaction force. First, we can use the sigma moment at A equals to 0. We have RBYL minus WA times A over 2 equals to 0. This one, RBYL, RBY times L, this one. And minus WA times A over 2. Why it is minus? Because it is moving clockwise direction. Since we have the counterclockwise direction is positive. Next, we have RBY equals to WA times A over 2L, and we have RBY equals to 1 over 6 WA. Next, we can have the RAY by using sigma Fy equals to 0. So we have this equation RAY plus RBY minus WA equals to 0. So we have know that RBY is equals to 1 over 6 WA. So we just substitute to this equation. So we have this one. RAY plus 1 over 6 WA minus WA equals to 0. And then we have RAY equals to 5 over 6 WA. And for the sigma Fx equals to 0, we just have RAX equals to 0, this one. And there is no reaction force other than RAX. So we have RAX equals to 0. Next step is find the elastic curve using superposition method. For the superposition method, we should divide the beam into two or more parts to make the analysis is more simpler. So the first condition is we have the boundary to 0 to A, we have this one, distributed force, and the condition 2 is for from A to L, like this one, the free body diagram. Okay, first we should solve for the condition 1. So for the condition 1 is the boundary is from 0 to A, which has the free body diagram like this. And we can start from the sigma moment at J equals to 0. So we have M minus RIX plus WX times X over 2 equals to 0. And we have M equals to Ri times X minus 1 over 2 Wx to the power of 2. So for the elastic curve formula, we have EI times d to the power of 2y per over dx square equals to Rix minus 1 over 2 wx square. For for the Rix minus 1 over 2 wx square is we we choose we take from this one for this equation. Okay, next we have EI times dy over dx means that it is we integrate the previous equation, this equation, we integrate it, and we have EI times dy over dx equals to 1 over 2 or Ix square minus 1 over 6 Wx cubic plus C1. Next, we integrate again this equation so we can have y here, y. So we have EI times y equals to 1 over 6 or Ix cubic minus 1 over 24 Wx to the power of 4 plus C1x plus C2. So solve for the x equals to 0, y equals to 0 to have the C2. So like this one. We just substitute the x equals to 0, y equals to 0. We have EI times 0, 1 over 6 s Ri x is 0. So we have 0 and 0, 0. So we have C2 equals to 0. Next for the EI, so we have EI times y equals to 1 over 6 or Ix cubic minus 1 over 24 Wx to the power of 4 plus C1x. And for the EI times dy over dx, we have 1 over 2 or Ix square minus 1 over 6 Wx cubic plus C1. Next, we're solving for the condition 2. We have the boundary x from A to L, the free body diagram like this. And same like the previous one, we can determine it from the sigma moment. So we have sigma moment at k equals to 0 here. And we have minus m plus rb times L minus x equals to 0. Minus m it is because the m is directed to the clockwise and plus rb it is counterclockwise. So we have m equals to rb times L minus x. So solving for the curve formula, elastic curve formula, we have EI times d square y over dx square equals to RB L minus x. Then we integrate this equation. We have EI dy over dx equals to minus 1 over 2 RB L minus x square plus C3. And then we integrate again this equation. So we have EI times y equals to 1 over 6 RB times L minus x to the power of 3 plus C3x plus C4. And for the boundary condition, we have x equals to L, y equals to 0. So for the boundary condition, we can have the C4. We can determine the C4, which we just substitute the x equals to L, y equals to 0. So we have 0 equals to 0 plus C3 L plus C4. So we have C4 is equals to minus C3 L. After we solve all of that, so we have EIY is equals to 1 over 6 RB L minus x to the power of 3 minus C3 L minus x. So for the EI dy dx, we have minus 1 over 2 RB L minus x squared plus C3. Next, we solve for the condition at x equals to 0, dy over dx equals to dy over dx. We have 1 over 2 RA squared minus 1 over 6 WA cubed plus C1 equals to minus 1 over 2 RB 2A squared plus C3. And then we have C3 equals to C1 plus 1 over 2 RAA squared minus 1 over 6 WA cubed plus 1 over 2 RB 2A squared equals to C1 plus 7 over 12 WA to the power of 3. And for the condition x equals to a, y equals to y, we have 1 over 6 RA a cubed minus 1 over 24 WA to the power of 4 plus C1a equals to 1 over 6 RB 2A cubed minus C1 plus 7 over 12 WA to the power of 3 times 2A. And then we have 3C1a equals to minus 1 over 6 RAA cubed plus 1 over 24 WA to the power of 4 plus 1 over 6 RB 2A cubed minus 7 over 12 WA squared times 2A. And then we substitute the RA and RB from the first calculation, which is the reaction force calculation, and we have RA equals to 5 over 6 WA and RB is equals to 1 over 6 WA. And we substitute and we have minus 25 over 24 WA to the power of 4, this one. And then we can solve for the C1 is equals to 12 over 72 WA cubed. And for the boundary 0 to A, we have EI times Y equals to 5 over 6 WAX cubed minus 1 over 24 WX to the power of 4 minus 25 over 72 WA to the power of 3x. And then for the dy dx, we have 5 over 12 WAX squared minus 1 over 6 WX to the power of 3 minus 25 over 72 WA cubed. And the data that we have is we have W is equals to 50 times 10 cube Newton per meter. A equals to 2 meter. E equals to 200 times 10 to the power of 9 PA. And I is equals to 84.9 times 10 to the power of minus 6 meter to the power of 4. So we have E times I is 16.98 times 10 to the power of 6 Newton times meter square. And after we have the data, we can solve the slope at A using x equals to 0. So we have EI times dy dx equals to 5 over 12 WAX squared minus 1 over 6 WX to the power of 3 minus 12 over 72 WA cubed. And for the condition dy dx is at A, which is x equal to 0, the slope. So we have like this. EI is equals to 16.98 times 10 to the power of 6 equals to 0 because we substitute x to equals to 0. So if this one is 0 and substitute w and substitute a, which is equals to 2 meter. So if minus 25 over 72 times 50 times 10 cube times 2 cube. And then we have this one. The slope is equals to minus 8.18 times 10 to the power of minus 3 rad. In step 6, solving the deflection at C, we have x is equals to 2 meter, right? Because x is equals to A at the question. So we have EI times YC equals to 5 over 36 WA to the power of 4 minus 1 over 24 WA to the power of 4 minus 25 over 72 WA to the power of 4. So we have minus 1 over 4 WA to the power of 4. And then we substitute again the EI, the W, and the A. We have this one, 16.98 times 10 to the power of 6 YC equals to minus 1 over 4, 50 times 10 to the power of 3, and 2 to the power of 4. So we have the deflection of the point C at the point C, which is minus 11.78 times 10 to the power of minus 3 meter, and it is downward. Yes, we already solved the question. So we go to the next case, which is the case study 2. We have the floor cantilever beam and loading shown. Determine the slope and deflection at NC. Use E equals to 200 GPa. Same like the previous one, we have the strategy to solve this question. First, we identify the knowns. Second, draw the FBD and calculate the reaction force. Third, divide the beam using superposition method. Fourth, find the concentrated load using the appendix formula. Fifth, find the slope and the deflection. In this case, we have the cantilever beam, which is the S 100 times 11.5. And we have known E equals to 200 times 10 to the power of 9 PA. And since it is wide flange beam, S 100 times 11.5. We can take a look at the appendix. We have the inertia of this wide flange beam is 2.52 times 10 to the power of 6 millimeter 4, millimeter to the power of 4. So, or it is equals to 2.52 times 10 to the power of minus 6 meter to the power of 4. Step 2, we draw the free body diagram of the beam. This one is the free body diagram of the beam. We have 3 Newton here, 3 Newton here. This is 0 0.5, this one is 0 0.75 from A to B. And we ask to determine the slope at C and the deflection at C. Next, we divide the beam using superposition method. For the superposition method, we can use two conditions like this one. Condition 1, we have the concentrated load at B, and the second condition, we have the concentrated load at C, which is the same, 3 kilonewton. Next, we find the concentrated load at the beam. So for in this case, we should take a look at the appendix, and especially for the appendix D. And why we should take a look at the appendix? Because in the appendix, we have the maximum deflection, slope at n, and equation of elastic curve formula to solve the unknown. And then we can solve for condition 1, portion A to B, which is this one, the free body diagram. And concentrated load at B, we have theta prime B is equals to minus PL square over 2 EI, which is we get it from this one, is equals to minus 3 0.75 square over 2 EI. It is equals to minus 0.84375 over EI. And for the YB prime, it is equals to minus PL cube over 3 EI, which is we get it from this one, is equals to minus 3 0.75 cube over 3 EI equals to minus 0.421875 over EI. Since the portion BC remains straight, and then we have theta C prime, it is equals to theta P prime, which is minus 0.84375 over EI. This one. And for the YC prime is also equals to YB prime minus 0.5 theta B prime is equals to 0.8484375 over EI. Still, we find the concentrated load, but it is for the condition 2. It is the concentrated load at C, 3 kilonewton. We have theta A double prime is equals to minus PL square over 2 EI equals to minus 3 times 1 over 1 times 1,25 square over 2 EI equals to minus 232,34375 over EI. And for the Y A double prime is equals to minus PL cube over 3 EI is equals to minus 3 1.25 cube over 3 EI, and it is equals to minus 1.983125 over EI. And since portion AB remains straight, so we have theta A prime is equals to theta B prime, which is minus 0.84375 over EI. And for the deflection as A, YA prime is equals to YB prime minus 0.5 times times theta B prime is equals to minus 0.84375 over EI. And after that, we have the data, which is E equals to 200 times 10 to the power of 9 PA. I, since it is wide flange beam, as 100 times 11.5, and we have I is equals to 2.5 times 10 to the power of minus 6 meter to the power of 4. And for the EI, means E times I is equals to 504 kilonewton meter square. And the last step, which is step 5, is find the slope and deflection at point C. By using superposition, we can have the slope at A and deflection at A. So we have slope at A is equals to theta A prime plus theta A double prime, which is equals to minus 0.84375 over EI, which is we have this equation from the previous one. We just substitute again, and this one also from the previous one, which is minus 2.34375 over EI. And after we sum it, we have minus 3.1875 over EI. And for the YA, which is the deflection at A, is equals to YA prime plus YE double prime is equals to minus 0.84375 over EI plus minus 1.953125 over EI. This one also from the previous equation, this one also from the previous equation. We just substitute again. And after that, we have the YA, or the deflection at A, is minus 2.796875 over EI. And recall that theta C is equals to theta B and equal to theta A. And also, the deflection at C is equals to deflection at B and equals to deflection at A. And then we can solve the slope at C using this equation, right? Because it is equals this equation. So we have minus 3.1875 over EI is equals to minus 31875 over 504, which is we get it from this one, the EI 504 kilonewton meter square, and the results is this one, minus 6.32 times 10 to the power of minus 3 rad. Also for the deflection at C, because deflection at C is equal to deflection at A, we can use this equation. This equation, we have minus 2.796875 over EI is equals to minus 2.796875 over 504, which is equals to minus 5.55 times 10 to the power of minus 3 meter. Okay, thank you for your attention. I hope this video will help you to solve that kind of problem, which is deflection at the beam. And I'm Muhammad Alfir Ramlani. Thank you and see you next time.